This problem is about getting the Q of a step in a cyclic process from the PV diagram. A closed system consisting of an ideal gas undergoes a cycle shown in the figure below. For the process 1 to 2, which one of the statements is true? That is, we have this process 1 to 2 and 2 to 3 and again 3 to 1. So it is a thermodynamic cycle. So we need to find the heat transfer during the step 1 to 2 out of this. Otherwise, we have to choose this heat transfer. Which one is correct? So how to start this problem? Now, whenever you are given with this diagram, of course, we can easily say the area enclosed by this curve is nothing but the net work obtained in the cycle. Network. And what about delta U for the cycle? Delta U is simply 0. And what is Q? Q also you can simply, Q is equal to simply minus W. So otherwise, this diagram gives you about the net work as well as net heat transfer. And yeah, and also we can also get to know something about from these values of these points. No, that is, this point is simply what is this point? It is PV, and this also is 2P times V by 2. So always this also PV, and it is given that it is ideal gas. Now for a ideal gas, PV V equal to simply RT. Otherwise, this point is also PV. This point is also PV. Of course, this point in the process it is not PV. Otherwise, the starting and ending points are simply equal to PV. Of course, PV equal to RT for the ideal gas. Irrespective of any process, whatever is happening on the ideal gas, you can simply equate that to RT. So at this point, it is RT, and this point is also RT. Of course, these two points are at the same temperature. Always PV of this one and PV of this two are the same, which indicates PV equal to RT for a ideal gas. These 2 points are at the same temperature. That's what we are concluding. And why it is needed, no? So we'll come to that. So we have this representation of this process 1, 2, 3, and V. This is half of that, and P and double of that. Okay. Work of this cycle is already, as I discussed, it is simply minus of P. It is simply the area enclosed by the circle, and what is this direction of the arrows? It is a clockwise arrows. So of course the arrows of this PV diagram also matter. Otherwise it is indicating a power cycle. Now in the Carnot cycle, now we used to draw this. No, there is what is it? The Carnot cycle has isothermal expansion and adiabatic isothermal heat. Yeah, I will. At least for convenience, I will also represent this Carnot cycle for your matching. Okay, otherwise we have this kind of cycle now. So otherwise we have a, so otherwise this is your a rough sketch for the Carnot cycle. Otherwise we have this clockwise direction of arrows. Now Carnot cycle is Carnot engine, which is producing work by taking the heat. It is taking heat at high temperature and rejecting heat at low temperature. So working between two temperatures, and as like this is also a power cycle. Otherwise, we have this clockwise direction of arrows. To match with that only we have said about this Carnot cycle. Okay. Otherwise, this is a power cycle. So for the power cycle, what is it? Will be the cycle is system is delivering work, and our convention is like delta U equal to Q plus W. In that, there is W ordered to the system is positive and Q ordered to the system is positive. Whereas in this power cycle, Q is ordered to the system. Of course, work is done by the system. So otherwise, the value will be coming as negative. Now you may ask for this area why to take this negative. No, it is simply area is half of this half P or is half BH. No, area of the triangle. No, area of this triangle you can estimate. So that triangle is what is this area? This otherwise you can take this as base or this as base. So it is going to be half into PV, and minus is included here because of the clockwise direction of arrows. and clockwise direction of arrows is for a engine. So engine is producing work, or otherwise what is a confined system, that thermodynamic system inside the engine is actually working against the surroundings. So always its energy current is reduced. Always W for the system is minus. Okay, that's why I'm having minus here. So always net work done by the cycle. Fine. So now of course what is interest we need to get is what is the Q for this step. Of course, just to say about this is a power cycle. I have discussed this. Okay, now what is the work? We can, from this diagram we can get to know the work. Otherwise, PV diagram is giving you the work. Otherwise, area enclosed by this, no. Otherwise, W equal to minus integral of PdV for a closed cycle. For a closed system. And what is this W equal to minus integral of PdV is simply the area under the curve. Otherwise, for the process 1 to 2, if you want to find the area, so that is simply the area below this portion, or is for the process 1 to 2. Okay. So always why we are interested in getting 1 to know 1 to 2, or is we need to know the heat transfer in the step 1 to 2. So work of the step first we can find, and we can get to know about heat. So work for this thing 1 to 2, work for this step. No, this is 1 to 2. You can get it from this total area minus this area. This area already we have this value. Okay, so the total area is simply V, it is 0.5 V into point, that this side is simply 0.5 V, no? And this height, total height is 2P. So 0.5 V times 2P. That is, we are getting this total area. From that, we already know this area, that is simply 0.25 PV. So area of this rectangle is this is 0.5 times 2, so always simply PV, and this is already 0.25 PV. So always this area is simply always this is 0.25 PV, this is simply 0.75 PV. Because this is also 0.25 PV, and this area and this area are the same because of course not visually, you can simply make use of this PV values. Okay, so we have this area is PV. Again, you may ask why this is having positive. Positive, why it is? Because here, this is this process 1 to 2 is a compression process, no? Otherwise, we are reducing the volume as well as increasing the pressure. Otherwise, this is in this process to the system work is added. So in our convention, we will be taking whatever is added to the system is positive. So 0.75 PV is the work added to the system. Okay. So that is 1 to 2 is compression because of. Okay. Now, for a step, delta U equal to Q plus W. So what is required is Q of 1 to 2. So we know this W of 1 to 2. What about delta U 1 to 2? Delta U for the process 1 to 2. So this, as I already said, this is having PV, and this point is also having 2P times V by 2, that is also equal to PV. So always these 2 points are having the same PV, which indicates T is constant. Always T of this 1 and T of this 2 are the same. Of course, the process may be like this. So sorry, already the process is given, right? Of course, if you want to construct a isotherm will go like this. So always this is your isotherm. So always these 2 temperatures are known. So in what way it is going to help us? Always these 2 temperatures are the same. We know for a ideal gas, delta U is simply a function of delta U is simply a function of temperature alone. U is T1 and T2 are the same. Since there is no change in temperature between 1 and 2, delta U is simply 0. That is, delta U depends only on the initial and final states. So we know the delta U of 1 and 2, U of 1 and 2 are the same because of same temperature. So delta U is 0. So now done. So delta U is 0 and Q is needed, W is available. So from that directly minus 0.75 PV. So what is the meaning of this negative? Heat is going out from the system, or is heat is rejected by the amount 0.75 PV. So there are options: heat added, rejected. So always it is answer is heat rejected by the amount 0.75 PV. So always what is the answer? Correct. This is the so always in approaching this problem, always you can easily get that network. And also additionally, because of these PV values, you can also look for this equality of PV. No, always at this point, these 2 points are having same PV. So that means these 2 points are at the same temperature. And for, since the temperature is the same, delta U is the same, so delta U equal to 0 for this process. And from the value of work, we can simply say about heat. That's what we have done. And to say how to say it is heat rejected or added for compression work is done on the system, and for keeping it isothermally, there should be a heat rejection. Always delta U equal to Q plus W. W is positive, Q should be negative. Correct?